Okay, so hi everyone. Today we're going to see something different because it's not going to be a regular video where I record myself creating some intuition or solution for a problem, basically a lead code problem. But this time I have something different, something new, and that is the KMP algorithm. I'm not going to go much into deeper about solving a problem or explaining my intuition. I'll be just going deeper into the KMP algorithm. The reason for this video would be that I want to revise this algorithm. I find it very difficult for to grasp this algorithm. It took me some time. I think 2 days, regular days. Well, obviously giving 2-3 hours on each day, and still I didn't had my concepts clear. But now I think they are, and I want to lock that straight in so that if I want to revise further on, I can. Okay, so let's directly jump into the algorithm. So first of all, what is KMP algorithm? Why it is used? So it is used for a purpose called string matching, right? It's a very popular problem in computer science and in software engineering because I think if we want to find a substring in a string, it's a very popular problem and a very common problem. For example, if we are searching on Google, it will have string matching algorithm, right? Because it wants to give you some suggestions. And for example, if we are searching for some keyword in a book, like we say just control find and find that keyword or find that line in a book, that is some string matching algorithm. And so basically string matching algorithm is very popular, and there are three algorithms. So one is naive algorithm. As far as I know, there are three algorithms. There can be more, I don't know. And then we have Rabin Karp algorithm, and then we have KMP. KMP means Knuth, Morris, Pratt. And this KMP algorithm is named after the scientists. So these are basically the last names or maybe the first names, I don't know, of the scientists who have created this algorithm. So naive algorithm has a very bad time complexity. It has a time complexity of like n into m, right? Because for every, let's say you have this string a b c, and you are finding ab. So for every instance, for every character, it will start from this character onwards, that if that string exists or not. So for example, we have this AB. We are on A currently, and it will search for, okay, A is fine, B is fine. Okay, so we have a string with this index that is starting with 0. And then we will shift this pointer to this part, and then we will see, are they matching? No. Then we will shift this pointer to this part. Are they matching? Yes. And then it is 2. And then we'll shift this pointer to this part. Are they matching? No. This part, are they matching? No. So basically this is what the algorithm is, and you can see it could be a laborious work because we are not, and you can see that there are some optimizations that could have been done, but it's not. So the time complexity of, just a second. Yes, so the time complexity for the naive part, you can see that for every, in the worst case, there is a possibility that for every character of the string S and the pattern, at every character you are trying to search that pattern, which means it is going to give you for every character of S, that is n characters and m characters. For every character n, you might be iterating for m times, which means it's of n into m. So the naive algorithm has a time complexity of n into m, right, which is not very optimized, I think, because strings are basically of very large character. They have very large characters in each. The number of elements are very large. So in that scenario, n into m would be a very expensive trade-off, so we don't want that, right? So then we optimize it to Rabin-Karp. Now Rabin-Karp use a concept of rolling hash. I find, like personally, I find Rabin-Karp much easier than Knuth Morris. That is why I'm not creating a video of Rabin-Karp. But Rabin-Karp works on the rolling hash feature, and this says that if you have a hash that is related to the string, that is equal to the string, then we need to check only that string which has its hash equal to the pattern, only that part of the string that has its hash equal to the pattern. And in that way, the average time complexity, theta of n plus m, right, this is the average time complexity in that way, in the Rabin-Karp. But in the worst case, when when we, like, every string is equal and we are finding for a, in that case we will be checking this one because the rolling hash is equal to it. and then we'll be checking this one. So then it becomes a naive algorithm, right? So the time complexity will be n into m. This is the worst case, and this is the average case. Because the average case is very much lower, so it makes sense to. I think the average case would also be similar to it, but on the like hypothetical average case, when you don't have every pattern matching with every index of the character, in that way it is going to perform little better. That is n plus m linear. But in Knuth Morris Pratt KMP algorithm, even in the worst case, it assures you that it will be a linear algorithm, which is mind blowing. But it does require some pre-processing. And we will see what is pre-processing, what do we mean by this pre-processing, how are we going to use that pre-processing data, and everything. We are going to see it. So now this is the formal context and background to this. Yes. So now let's jump to the main part. That is, what is KMP? How does it work? So let's say you have these strings. Let me take this example. Yes. So you have this A, D, S, G, W, A, D, S, X, D, S, G, W, A, D, S, G, Z, right? So this is the string, and the pattern that you are looking for is this pattern, right? So this is the pattern that you're looking for. So this is your string and this is your pattern. Now the task that is given to us, you need to find those indexes where you can find this pattern. So in the whole string, you can see that the indexes are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So in the whole string, you can see the pattern is only available at this point because we have copied it from here. So this is 9, and your answer should be 9, right? Because starting from the 9 index, you can find this pattern. Now, how we can work with this? Now let's start as a naive implementation, right? So let's compare these characters. So we are comparing these characters that are right under the string, and you will see that A is not matching with this. Because A is not matching with this, we will shift this string to the next part. So now this string is pointing at this string, right? Is D matching? Yes, it is matching. Is S matching? Yes, it is matching. Do we have G matching? Yes. W, A, D, S is matching. And then, yes, here is the problem, right? It is not matching. G and X are not matching. Now, when we encounter that the whole pattern is not found in the string, then what we do in the naive part, we just simply move the string to this character, and then we are trying to match D and S. Okay, it doesn't match. Then we try to match D and G, it doesn't match, right? But we are not going to do that. What we are going to do it, what we do in the naive implementation is, let me just show you. I think you must have got the grasp of what I want to tell you in this case, but just an example. In naive pattern, we just move this string like this, and then because D and S is not matching, so we move this string like this. D and G is also not matching, we move this string. D and W is also not matching, we move this string. D and right, and in this case, right, so in this case they are not matching, right? What I will do is, rather than playing with the string and doing that naive operation, which I know is not going to help us, can you observe that there is a pattern here? Can you observe that there is a pattern here? The pattern is, in this string, these strings before X, they are matching with the pattern, right? And why should I only increment this string by 1? The point is, D and S, they will match, right, regardless. And they should point here directly. Why can I not have them here directly? right? This is my question. Can I not have them there directly? The answer is yes, you can. And how we can do that? So we will use something called prefix suffix. So when we are at this point, we see that the string is not matching. Then the elements from this side and the elements from this side, if they are equal, if you can get some information from S, because that is the next element to G, that how many elements are similar, that is prefix and suffix that are similar and of longest length, because you want to reduce the redundant matching. To reduce that, you want to find the maximum length same prefix and suffix of the pattern, and this S will give you the information that D and S, ds string substring ds in this pattern and this substring ds, they are matching from the beginning. Like this S will say that okay, I have ds and I think I have seen ds at the beginning too, so I think that is the longest common suffix prefix that you can use. And I will say okay, I trust you, I trust you S, I have taken that advice, and now I will increment this pattern to that place, you know in order to save all my here. And you can see that I have saved these many computations. Can you just imagine how many redundant comparisons that we have saved us for ourselves? That is why this algorithm is very powerful and is very efficient. Even in the worst case, it's give you a linear solution. So now we are matching D and S, and because these two strings were same, now we are pointing at G, right? Because we need to check that element. And G and X are not equal. Now G and X are not equal, you will ask the next element that do we have any common prefix and suffix? No, we don't. S will say that I haven't seen S in the prefix, so we don't have any element. So because we don't have any element, then I will simply move this string to further part. I will simply move the string to the further part for further checking. And now I can see D and D is matching, S is matching, G is matching, W is matching, A, D, S, G, Z. All of the strings are matching, and now my index is pointing on the outside of the bounds of the pattern. When I am pointing on the outside bound of the pattern, then I will say that the string, the str where this pattern has been started matching, that is my answer, and my answer will be 9, right? Now you can see that there is some pre-processing that we need to do, because we won't be calculating the prefix and common or the maximum common length of the prefix and suffix at the runtime of the matching algorithm, because that will create a problem for us. Because in that case, for every element of the ith string of the string s string, we are making linear time in calculating the prefix and suffix. Why shouldn't we calculate prefix and common prefix and longest prefix and suffix for this pattern for every index earlier, in before making comparisons to the main string, right? That is the concept. So how this algorithm will work: first we will find the longest prefix suffix of the pattern. After finding this, we will have a vector which will have these values, that for this index, for this index, for this index, we have x value, y value, z value. X value, y value, z value means that you have this length of the like 2 length, like 0 length, and then you have 2 length, that is, or 1 length, then you have 0, 2, 3. So these numbers means that at this index you will find a common prefix and suffix. That means the substring that is starting from the beginning, and is also available at the start of the pattern, and the length of that, and the longest pattern, right? And the length of the longest pattern. These are these numbers. And from LPS you will simply run the naive algorithm. The naive algorithm will have this condition that if it is matching, and if at some point if it is not matching, then we just simply increment the ith pointer. But if it is not matching, then we need some conditions. The conditions will be if j is not equal to 0, which means that some strings are matching, right? Which means that some strings did match. And when this is the case, when some of the strings were matching, then we need to have the LPS of the previous string, right? Because that will give us the value that how many strings were matching, and how many redundant comparisons can we reduce with, right? That can only be known from the LPS array. But if the j is equal to 0, which means none of the strings were matching, which means we need to just simply increment the I, and that's it. This might be a very fast paced KMP algorithm because I think I'm only into 15 minutes and I'm done with the algorithm. But I think with implementation, it will be more clear. I hope so. And let's start this. So, first of all, include bits std, and then you have using namespace std, then you have int main function, and in this main function, you have a string that is s, the main string, and you have a pattern, and then you are taking the values. After taking their values, now you will have a vector of int that is lps, and this lps will be equal to pre-process string, right? This function, we will create this function, by the way. So this function will have the argument as a pattern, and that's it. And then you have a vector of int, and that is answer, which will contain all the indexes where the substring could be found, and that will be KMP find pattern KMP by KMP algorithm. So this will have string, then it will have a pattern, and it will also have LPS array, right? And then we'll simply print the pattern. So and then return 0, and that's it. So now let's build these functions. So first of all, we have a vector int return type for pre-process string, and it is taking the reference of the string, that is the pattern. And in this pattern we have yes, so first of all we need to have the size. So size will be m, and it is equal to p dot size. Then you need to have a vector which you need to return, right? LPS, and the size will be m and initialize with 0. And then you have int I, that we will use to iterate over the string, that is equal to 1. And the reason we are having this one, I will explain you now. And then we have length, that is 0. So now we are going to do some prefix and suffix matching. Let's say you have this string ABC, right? And now I have asked you, let's say this is AB. Yeah, let's just take this example. So you have DS GW AD SGZ, right? So this is the string that is given to you, the pattern. And in this pattern, you need to create the LPS arrays. How we can create the LPS array? So you have these indexes 0, 1, 2, 3, 4, 5, 6, 7, 8. And this is the LPS array. Fine. Now in this LPS array, at 0th index, you are given D. So let's study this character or this string D. So how many prefix are there? One is an empty string that will always be there, and then you cannot have the last character, right? So which means we only have the empty string as the prefix. Now for suffix, you can have this D, which means, well, empty string will be there regardless, and then you have this D, and these are only the suffix. Now in this prefix and suffix, what is the common string and the longest one as well? The common and the longest string is this one, that is the empty string. And what is the length of the empty string? That is 0. So you will have 0 here. Now you have D and S. So for D and S, you will have a prefix of empty string and D. And for the suffix part, for this part, you will have D and you will have S, right? Yes, you will have DS and then you will have S. Now, what is the common and the longest string? That is again the empty string. So you will have 0 here. Then for G, DSG, right? You have DSG. Now you have D, then you have DS, and the same case goes here. Now you have G, then you have SG, then you have ds, right? And in this case, sorry, now you have dsg, not ds. Yes, dsg. Can you tell me what is the common string and the longest one as well? That is again the uh, empty string, that is the length 0. And then you have this w, which means that this is now dsg, right? And in this case, this string will be, we have w, then we have gw, then we have sgw, then we have dsgw, right? And in this case, you can see that what is the string that is matching? Again, it's the empty string. So you have this 0, and then now you have a. So for the prefix part, you have dsgw, right? And for the suffix part, you will have these elements as, so you have a, then you have wa, then you have gwa, then you have sgwa, and then you have dsgwa, right? And if you can observe, then there is no string that is matching with, there is no prefix and suffix matching string other than the empty string, which means here will be 0 again. And then you have this ad, right? And in this part, you will have this as dsgwa, and for the suffix part, you will have these strings as, yeah, I should move this a little bit. Yes. And for the suffix part, you will have d, then you have ad, then you have wad, then you have gwad, then you have sgwad, then you have dsgwad, right? And in these strings, can you see any string that is matching with itself? Yes, we can now. And that is this d. So d is matching, right? If d is matching, in that case you will write 1 here, because d is the only, like, there are empty string and d, but the longest length is 1 and this length will be 0. So that is why we are using d length, that is 1, because we need the longest matching length. And now you have s. I think now you can understand that with s, this string will look like this. And in the prefix part, I'm not going to create all of the strings again, but you will see that you have something like this ds that is matching with this ds, so the length will be 2, right? So this is the main point. What I, what do I want to say at this point is that this is how an lps string is, lps array is created. For every index, we write the longest prefix and suffix string, substring, that we have found in that pattern. So that is how we create an lps array. Now the naive implementation of an lps array would be nq, right? Because for every character, of the pattern, not n cube, actually m cube, because that is the size of the pattern. And yeah, so what we are doing is, for every character we are iterating over the string once, and then we are iterating over the string again, right? Which makes it a very bad algorithm, but for conceptual understanding part, it is, I think, a very good illustration. But we can obviously optimize it, further with the help of the previous case. So for example, in this case, you can see that there was 1, and the new incoming character, that was s, is also matching with the is also, yes, it's also matching with the length, right? We have 2 pointers. So one was this matching, so now we increment the pointer, and now we are at this. Now s is also matching, which means that the previous suffix, which was also matching, and the current element is also contributing in the matching of the new substring. So the previous length will be incremented, and the length is now going to be 2, right? This is the main concept of doing this algorithm in linear time. To use the, if you already have some matching algorithm, if you already have some lps built up, and the current element is also equal to the comparison character, in that case, you can increment the length of the LPS that you have found for the earlier element, for the previous character. The current character will have its contribution and increment the length of the LPS, right? Yeah, you can see that in G, when you have G, you will see that the pointer was like this. Now you increment this pointer and you increment this pointer. You will see that G is also matching. So if G is also matching and the S value was equal to 2, then this string is now going to be 3. So you will write 3 here, right? You don't want to calculate again and again, right? You don't want to calculate for G, that you want to calculate, okay, DS, and then you have DSG, WDSG, and AD, right? You don't want to do that, because that will be a knife, that will be an M cube. Yeah, it should be M as well. That will be an M cube algorithm, and you don't want this high much, this much high time complexity for the pattern LPS constructing. You want it to be linear, right? That only then in that case you would be able to solve it in linear time. So yeah, so this was the case, and now you are on this, that is Z. Now W and Z, they are not matching, which means that if you have these characters, then they will not give you the length. They will not, the length will be resetted and the LPS value for this character will be 0, right? And you can also see that by yourself, that if you want to construct some prefixes or suffix, yeah, actually no, it won't be 0. It's my bad, it won't be 0 if they are not matching, right? In that case, the length that you have constructed till now will be equal to it, and that is the uh, just a second. So we have this I that is pointing on there, and we have length G and W, they are not matching, and but length is equal to 3. So yeah, so length is equal to 3 at this point, right? So G and W, they are not matching. Length is equal to 3. These are the 3 characters that are matching. And you will say that find in the LPS vector length -1. So why do we say -1? Because 3 strings are matching, right? And in 3 strings, the incoming character is having a negative contribution. So because of that, you need to check the previous value, and that will be this value. So for this value, what is the LPS value of this value? 2, that is 0. That is why it will be equal to 0. And I was right. Yes. So this is your LPS array. And let's construct the LPS array. Let's continue constructing it. So we, you know what, let me just construct the KMP. I don't like this error squiggles. You have vector int, and you have find pattern KMP, and you have a string s, then you have a string pattern, then you have a vector of int reference LPS, and you are returning an empty vector just for now. Yes. Yeah, so now let's get back to the pre-processing part. So now you have these pointers, and mind it, if you have just simple one character, it will have an LPS of 0. You can try it out. The prefix will be, I think I've shown you in the video that it will be an empty string, that the length of the empty string will be noted, which is why it's 0. Now you have while I is less than m, right? The size of the string, because I is the pointer that is iterating over the string or the pattern. And now there's a case, if the characters are matching. If the characters are matching, in that case it's fine, just increment it, right? Just increment the length variables, which means pattern of I is matching with the pattern of length. So length is used as the LPS length, the common prefix suffix length, which we are using, and length is that pointer that is pointing on the string. So LPS of I plus plus, and yes, and length plus plus of length, right? Now another case is, now this else case. So this else case is if characters are not matching. If they are not matching, then we have two conditions. So one is if there are any other previous characters that are matching. If length is not equal to 0, which means there are some previous characters that are matching that have some LPS value. And in that case, I will say length is equal to LPS of length minus 1, the previous character's LPS value. Otherwise, I will say else, if there are no previous characters, then we will simply say that LPS of I plus plus, the current character of the pattern, is equal to 0. That's it, and move our I pointer. And in the next step, I will just simply return the LPS array, right? Now for the debugging part, let's see if we are getting the right LPS array or not. So I is equal to then let's just say LPL only, LPS, and C out. Okay, so for this array, we are getting the exact LPS value that we have. Jesus, man. All the calls that I'm getting in while recording a video. A very good luck. Yeah, so back to the video. Now we have, yes. So now we have constructed a pre-processing string function, right, which is required to create an LPS array. And this is the LPS array that we are getting. And so this is something that we are doing for verification, that if we are getting the correct LPS array or not. And at this point, you can see that it is the correct LPS array. So we can rest assured that the pre-processing function is doing fine, and now we can implement the find pattern function, which is based on the KMP. So let's see how we will do it. So this is the case, right? We have this string. Yes, we have this string, and this is the pattern. So it's a very simple observation that we will start matching the first character, and if it is matched, then fine. Then we will increase the length. Then we will increase not the length, but we will increase our pointer and keep on matching it. And if we don't find, and if we find a character in between that is not matching, then we will ask for the LPS, which will give us the longest prefix suffix string. And in from that value we can reduce the redundant searches or comparisons that we don't require to make, right? And that is the whole point of using the KMP algorithm, to avoid that redundant comparisons between the characters that are already equal. Why are we comparing them again? So first of all, we need to have the size. So I will say s dot size. Then we have variables I is equal to 0 and j is equal to 0. Yes, now we have a while loop. I is less than n, that is the size of the string. And in this loop we have first thing. So first thing is if the characters are matching, right, which means s of I is equal to p of the pattern of j. So if this is the case, then fine, just increment it, right? Just simply increment it. Otherwise, if they, now the thing is, if they are same, we are incrementing it, fine. This is a one thing. Another thing is, if I is equal to, after incrementing it, or sorry, j, if j becomes m, and we also need m here. Yes. Now if j becomes m, which means the whole pattern exists at that string, and this is the case where we realize that we have gotten our answer, and answer will be not answer but the vector int answer, and answer dot pushback. Now in order to get the value of answer, so let's say we are at this point, right, and the size of the string is 0 1 1 2 3 4 5 6 7 8 9. So this is the size of the string is 9. Now in order to, and we are pointing on this ninth index, right, and in order to get this value, what I'll do is, and my j, actually my I pointer is pointing on 18th value, so I will simply say I minus of j, this will give me the value of 9, which is the answer. So I will say I minus of j. This is the first thing. And another thing is j should be equal to LPS of j minus 1, right? It's good to use LPS of j minus 1 because we, in a naive approach, what we do is if we find the answer, if we find the array, then fine, then just increment the ith pointer and start. So increment this pointer and start searching from this side. Rather than doing it, we can use the LPS concept again. So if we have some strings matching, if we have some prefix suffix that are common, then we can find the longest length and reduce the searches of that length. Otherwise, now another condition is else if I is less than n, so I should be less than n, and s of I is not equal to p of j, sorry, right? This is another main condition. And in this condition, we will have if j is not equal to 0, which means that there are some characters that are matching it. Then we will say that j is equal to LPS of j minus 1, because there are some characters, right? So that is why we can do j minus 1. Otherwise, if there are no characters, then we will simply just increment the I pointer, because now at this point we can do nothing of it. So we just simply increment the I pointer. And at last, I will say return answer, the vector that we have created. And yes, now I think we don't need to print the LPS array. We can run this. And okay, it's taking a lot of time. Am I doing anything wrong? Wow, 480 milliseconds. That's not justifiable. Okay, now it's fine. I think it must be something like the cache problem with the compiler. But anyways, it's working fine. 58 milliseconds. This is a test case. Let's write a new test case. Um, so the string is this, and we have AS, and AS comes at this point. Okay, this point. So let's see what will be the input. I think it should be 3, 4 indices. Okay, it's at 0. So AS, fine. Then it is at 0, 1, 2, 3, 4. Very good. Then it is a 9. I think that's accurate. It's 15. Okay. Then it's 28. This must be here. And then we have 33. I think it's working fine. Yeah, I think it's working fine. So this is the algorithm. I think the some confusion would be there related to the part where why we are using the LPS of j minus 1. That's just one notation of saying that when we have some characters that are matching in the string, right? It's just a notation of saying that when we have some characters that are already matching in the string, and let's say you are at, so let's say this is the string. Yes, so this is a string, right? And using the LPS array is just a way of saying, for example, at this case, these characters were not matching, but these are matching, right? So LPS, using the LPS of j minus 1 means the characters that are matching, if there is any longest common prefix or suffix string, then why shouldn't we use it? Because if we use that string, then it's very much, why. Okay, so now this d value, the thing is, this d value, otherwise what we need to do is we will be shifting it here, then we will be shifting it here, then we will be shifting it here, right, in the naive approach. But now with using LPS of j minus 1, we can directly put this here. And why have we put this here? Because this was the suffix and this is the prefix. It's the same way of saying that this is the suffix and this is the prefix, right? I think it makes perfect sense. So why shouldn't we match the suffix and prefix in order to reduce the searches, in order to reduce the comparisons? That is the whole point of KMP algorithm, which makes it very powerful. Although there is like a thing like it requires linear, uh, it requires a linear time of for the pre-processing part, and the overall time complexity of the algorithm is also linear. It's, I think, n plus m. So yeah, this was the algorithm. The space complexity, so this is the time complexity, and space complexity is it's using an LPS array, that is the auxiliary array, and the LPS array will have the space of m, I mean theta of m. So yeah, this was the algorithm, and I hope that it was a good explanation. If it is not, then I might make a new video. I don't know, but I hope this was a good explanation because this algorithm has bugged me a lot. Like I spent a lot of my time on this algorithm. Why? I don't know why the LPS concept was so difficult for me to understand. But yeah, this was the algorithm. We might solve some questions on it. Anyways, thanks for watching, guys. Have a good day.